Energy requirements shift drastically depending on the task. A drone needs high power density to lift its own weight off the ground, while a heavy industrial forklift relies on raw, sustained energy to hoist dense payloads. When specifying a power source, there is a common trap. Assuming the most energy-dense, modern chemistry is automatically the correct choice for every application. The current industry consensus often treats lithium-ion as the undisputed standard, writing off lead-acid technology as an outdated relic. Yet, if you look at the back end of global infrastructure, you'll find that heavy, bulk stationary power systems still rely entirely on that older chemistry. This chart outlines the 6 core engineering parameters that dictate battery selection: capacity, weight, efficiency, cycle life, cost, and safety. Capacity serves as the baseline metric, the total amount of charge the battery can store. When we map this out, lithium batteries consistently show a higher capacity per unit volume than their lead-acid counterparts. If a project had infinite space and an unlimited budget, the specific chemistry wouldn't matter. But real-world engineering forces a strict compromise between a system's physical limits and its required performance. To understand the physical constraints of both chemistries, we can evaluate the energy density to weight ratio using a standard 35 amp-hour SLI capacity as our baseline. Storing that exact amount of energy in a lead-acid battery comes with a massive physical penalty. A 35 amp-hour lead-acid unit weighs at least 10 kilograms more than its equivalent lithium-ion counterpart. But weight is only part of the equation. We also have to calculate charging efficiency, which is the ratio of charge entering the battery during the charging phase compared to the amount of charge you get back out during discharge. This graph tracks efficiency against discharge rate. Lithium-ion maintains roughly 92% efficiency, while the lead-acid curve sits around 60%. But notice what happens as discharge accelerates. If a system demands rapid power, lead-acid's efficiency deteriorates quickly. To guarantee a specific power output from a low-efficiency chemistry, engineers have to employ a brute force workaround, oversizing the entire lead-acid battery bank to mathematically compensate for the expected energy loss. For weight-sensitive mobility applications, lithium's low mass and high efficiency make it mandatory. But if the machine you're designing sits firmly on the ground and total mass is irrelevant, bulking up a lead-acid bank is a completely valid engineering compromise. Securing lithium's lightweight performance requires absorbing a severe upfront capital expenditure. Looking at raw base unit pricing for similar output numbers, a lead-acid battery costing 3,000 rupees sits directly against an equivalent lithium-ion chemistry that can run as high as 20,000 rupees. To justify that multiple, we use this chart to plot upfront unit cost against total cycle life, meaning one full charge and discharge sequence. Lead-acid plots very low on the cost axis, but its lifespan plateaus at roughly 300 cycles. Reaching even those 300 cycles requires strict operational limits. The depth of discharge, the percentage of the battery drained before recharging, cannot safely exceed 50% for a standard lead-acid unit. Conversely, lithium-ion starts with a severe financial penalty, but it delivers 1,200 total cycles, and it does so while allowing a much deeper 80% depth of discharge. Specialized industrial chemistries like lithium titanate push this envelope even further, achieving life cycles well past 40,000 cycles. This graph tracks lithium costs dropping steeply from $1,200 down to $150 per kilowatt-hour by 2019, thanks to manufacturing advances. Compare that to the flat, unchanging line representing lead-acid, whose material supply chain bottomed out decades ago. Taking the initial capital hit on lithium only yields a positive return on investment if the hardware it's powering is engineered to survive long enough to utilize those thousands of cycles. Pushing maximum energy into the smallest possible physical footprint introduces serious mechanical risks, specifically regarding volatility and thermal safety. The primary threat is thermal runaway. This violent feedback loop occurs when localized heat triggers a rapid release of stored energy. In lithium cells, this failure is often initiated by overcharging. Repeated overcharging causes metallic dendrites to burrow across the electrodes until they physically puncture the separator membrane, triggering an immediate short circuit. Because lithium chemistries are so sensitive to charging conditions, the mandatory mitigation strategy requires integrating a complex battery management system. This electronic layer actively monitors voltage, current, and thermals. Lead-acid systems can also experience thermal failure, but it usually presents as a slow degradation. The rate of internal heat generation exceeds dissipation, causing the cells to dry out and the plastic containers to soften and melt. Moving from catastrophic failure to controlled end-of-life logistics, the recycling infrastructure presents another major operational difference. The lead-acid supply chain operates on a mature, well-established infrastructure, regularly recovering and reusing 90% of the battery's raw materials. Lithium recycling, by contrast, is still developing and highly fragmented. Lithium-ion provides immense power density, but demands constant electronic babysitting and complicates disposal. Lead-acid offers operational simplicity and closed-loop sustainability, assuming your system can afford to carry the heavy physical mass. Specifying power is rarely about choosing the absolute most advanced chemistry on the market. It is about matching the correct constraints to the system's operational envelope. We can visualize this specification process using a decision matrix, plotting a project's budget sensitivity against its weight sensitivity. In the high-performance, high-budget quadrant, we find applications like electric vehicles, drones, and aerospace components. For these mobility engineers, excess mass destroys their core system efficiency. The massive expense and the complexity of integrating a battery management system are entirely justified to shave off kilograms. Down in the high-budget sensitivity, low-weight sensitivity quadrant, the applications change to telecom towers, UPS server racks, and heavy industrial machinery. Infrastructure engineers often have abundant physical space. They cannot justify heavy capital expenditures for stationary mass, making lead-acid the logical specification. A complete technical specification has to account for the total cost of ownership. That means factoring in the upfront unit price, the integration of required management electronics, and the final logistical cost of disposal. Let the physical and economic realities of the machine dictate the power supply. Legacy technology remains deeply embedded in modern infrastructure because physics and budgets demand it.